Now I'm pleased to present Juan Rafael. I mean, we know Juan Rafael from the past, but we will have right now the seminar, technical seminar by Juan Rafael in frame of the meeting, our meeting. Juan Rafael originally studied at the National University here in Colombia, and then moved to Holland to make his master's degree program, or his master's degree, and also the PhD with Professor Bernard. And since then, he's working on star formation in Star Wars. So, Juan Rafael, thank you very much, Yuri. Thank you for coming.
And thank you for showing up. I know it's not easy to be here all day, but thanks for showing up for this talk. I wanted to tell you a little bit about the research I do. Some research that I started doing back in Leiden together with Bernard, as well as Brent Rhodes, who's now in Heidelberg, and more recently also together with some people at the CFA, where I've been doing a postdoc since about a year ago. By the way, this is not that I wanted to emphasize that I'm at the CFA, it's just a blue line that's by coincidence is there. Before I came here, I looked at the title slide and I realized that maybe it already sounds too serious. So I thought I would start just by telling you what this talk is going to be about. So basically, as you can see, I'm going to be talking about star formation, so how stars form. In a particular type of objects called starbursts, which are regions in some galaxies where the star formation efficiency is particularly enhanced by some physical conditions, and we're going to try to see why that will happen. And then this is a study that uses a multi-wave approach, which means we will be looking at different regions of the spectra in the ultraviolet, the mid-infrared, and far-infrared. And the Bayesian board refers to particular statistical methods that we use to extract as much information as we can from the data and the models we have to understand. The picture you see there is a beautiful interaction and a good example of what happens in a starburst when two galaxies collide, and the funneling of gas that produces that interaction boosts the star formation in these systems, and this is the kind of systems I'm interested in my research. So I'm going to give you a brief introduction about what I'm going to be talking about. I'm going to start with an introduction about what starbursts are and why we are interested in them, why we bother about studying them. Then I will tell you a little bit about the spectral energy distributions of these systems. How do they look as we look at them in different wavelengths of the spectrum, of the spectral window. And then I will introduce a tool that I started designing when I was a PhD student in Leiden, and I've been working on recently, to fit those spectral energy distributions of these objects using models and statistical methods to try to extract physical parameters from these systems, to try to understand physical conditions that we can relate to why stars form so quickly in these systems. And then I will apply that method to a few examples, interacting galaxies, some massive star formation regions in nearby, and also other types of starburst galaxies. I will try to put all that together into a conclusion about two different modes of star formation in the universe. And of course, we will have what we call a nyama, which is just a little bit of extra information about future observations with JWST. This is only because I had the pleasure to work together with Bernard also in the calibration of one of the instruments for the James Webb Space Telescope, and I will tell you a little bit about that.
Yeah.
Yes, I don't know how to translate that into English. I'm not sure that's the translation. So first of all, why do we care about star formation in galaxies or starbursts in the first place? So since the talk is going to end with JWST, let's also start the talk with JWST. JWST is a large telescope that is being built currently and that will be launched into space in 2018. And one of the main scientific goals that it has is to look back into the early universe and try to figure out how the first galaxies formed and how the galaxies that we see today were assembled together to end up the way we see them today in the local universe. And so if we want to understand how that process happened, and that's important just because most of the matter that we see in the universe today was formed, you know, in a particular portion of the history of the universe, and we want to understand how those galaxies formed. So it's very important to understand how the star content of the present universe formed by evolution of galaxies colliding, etc., etc. But more importantly, galaxy assembly is still happening today. We still see that galaxies are interacting and are forming new types of systems. And so by studying it, we're not only looking at the past and how those galaxies came together to form what we see today, but also we can tell a little bit about the future. Because as you know, probably, we will also be en route to collide with the Andromeda galaxy at some point. And so it's important to understand, for example, how the two galaxies collide and what happens with the star formation in galaxies when they collide. So this is just a motivation for the talk. And then, what are then these weird objects that we call starbursts? There is really not an overall definition that everyone agrees on, but we can try to describe it in terms of a transient episode of enhanced star formation efficiency. So basically, these are regions in the universe where at a certain moment in time, the rate at which the gas is turning to stars increases dramatically, and we can see that in many different ways. If we want to quantify that a little bit, we can use something called the gas depletion rate. So that basically, what that means is that you can measure the total amount of gas that you have in your galaxy, and you can try to figure out, if you look for that particular galaxy or system, how fast this gas is being turned into stars, how long it will take for that process of star formation to completely finish with the gas and form it into stars. And if that time is much less than the Hubble time, which is basically the age of the universe, then we're talking about a starburst. Just for example, in our galaxy is a galaxy that forms stars at a very peaceful rate, about 1 solar mass per year. So every year we have one new star in the galaxy. And if you calculate that depletion time, gas depletion time for the Milky Way, that's about 3 gigayears. So that's kind of comparable to the age of the universe, right? As you go to systems that are, let's say, more violent, for example, these two galaxies, N82 and R220, that are two good examples of local starburst galaxies that are not too far away, that depletion time is of the order of only 20 million years or 30 million years. So that's already significantly smaller than the Hubble time, and hence we can use that to define, to say that these galaxies are starbursts. But that's not only, that's not only for galaxies. There are also regions in some galaxies that are forming stars at particular regions. So they are not maybe entire galaxies, but specific regions within galaxies that are forming stars at particularly high efficiencies. For example, the 30 Dorados region in the Large Magellanic Cloud, not too far away from us, also has a depletion time of 10 million years, so we can consider it a starburst as well. This is an example of how a local starburst looks like. And what you can see there is a big mess of luminosity, a little bit hidden by large, amounts of dust. The reason why you see all those dark regions is because there's a lot of dust. That's the material together with the gas from which stars form. So you see there's a lot of dust involved. And what that means, and you will of course know now that we know about radiative transfer and these kind of things, that of course when the dust enters, when the dust reaches an equilibrium temperature, it emits light in infrared wavelengths. So these systems are very bright in the infrared and are usually associated with interactions, with very disturbed systems where you see that something has happened there, maybe two galaxies collide or something like that. It's very important to understand them because they tell us about the process of massive star formation. Massive stars much 8 times or larger than the Sun, need these kind of environments to come to exist. And so understanding these systems is very important to understand the formation of massive stars. But also, as I mentioned at the beginning, to understand the evolution of galaxy assembly in the universe. How do we study them, apart from looking at those very pretty images? I'm sorry, I forget that I have this thing. I'm going to use that. We don't have them in the States. So you can look at how these objects emit their light in different wavelengths. So what you see there is basically spectra of different types of galaxies, where you have here basically the wavelength and here you have the intensity of these different galaxies. And you can see that there's a change normal these galaxies, like for example the Milky Way or M101, which is this galaxy here, it looks like a normal spiral galaxy that has, this is the spectral energy distribution of the system. And you see that it has a considerable amount of emission in the optical and the UV. And then it also has some emission here in the far infrared that is related to certain amounts of dust that are mostly in the spiral arms that emit in the infrared and create that system. As you go to systems that form stars in a kind of a more violent way, like in the case of M82, you see that the contribution to the spectral energy distribution from thermal emission from the dust is considerably higher than in the case of M101, a normal galaxy. And when you go to very, very luminous systems like this one here, which by the way does not correspond to this galaxy here, but it's what we call an ultra-luminous infrared galaxy. It's a galaxy that has so much dust that is emitting huge amounts of gas. Not only it has dust, this dust is being heated by some process, most likely star formation, and it's completely dominated by the formation of, by the emission of far infrared wavelengths. But finally, through many processes, these galaxies also evolve into galaxies that have very little amount of dust left because it has been already consumed. Yes?
Well, in generally, the distribution is smooth, but what are the wiggles right in the middle?
This here?
Yes, right. What's that?
This is emission from a particular type of molecules called polycyclic aromatic hydrocarbons. And these are basically bands of emission that are related to transitions in these molecules. These are molecules made of carbon and hydrogen. And they vibrate in many different ways and rotate, and they produce these bands that are very important for us to understand, by the way, the star formation. I'll talk a little bit more about that later. And so you see that finally galaxies that have no dust left are, again, completely dominated by the optical and ultraviolet.
Sorry, they all behave the same way. That's why they are all having the same lines and curves.
Well, they behave in the same way in the sense that all the emission that you see there comes originally, or most of the emission that you see there, let's say, comes originally from young stars that are being formed. And that light is either directly transmitted to our telescopes, and that's the part that we can see in the optical, for example, or reprocessed by the dust that surrounds them, and then re-emitted at wavelengths in the infrared. So you see these two kind of, the typical structure of these two peaks, one related to the photosphere of the stars, so what we see from the stars directly, and then, of course, the reprocessed emission by dust that you see in this other peak. So that's why they all have similar. But of course, it's the ratio between those that changes from one to one, and also the properties of the emission lines that you don't see much here, but they also have emission lines related to the atomic material, etc. So these are the kind of things that we're interested in. We want to understand how much we can learn from those galaxies by looking at the. Get used to this. Okay, let's practice a little bit. So, but what triggers them? Why do these starbursts, these particular galaxies or regions where stars are being formed at such high rates? Why are they happening? So there has been, long-standing evidence that the systems that look more bright, that emit a lot of light in the infrared, are also morphologically very disturbed. So if you look at those systems in the universe that emit a lot of infrared light, they also happen to be the ones that look very disturbed morphologically. And people have related that to the fact that maybe these are just interacting systems, galaxies that are colliding, for example. And the collision somehow is responsible for this increase in the star formation efficiency. So the reason why that can happen could be, for example, because during the interaction, the gas loses a lot of angular momentum and collapses in large scales, and that collapse of the gas produces a lot of star formation. Now, this is just, and I think for this I need to go here, but this is just an example of how people try to understand the interaction between the two galaxies. You see there a simulation based on physics of two systems, and as the interaction goes by, you will also see comparison with real observations. So people have done a quite decent work at understanding how these collisions happen And you see that you can have a very decent comparison with observations, which is a good sign that we understand how these things are happening. So these, for example, these are mostly Hubble images of interacting galaxies that have a corresponding, snapshot in the simulation. So that's a very, very cool thing. So we think that these kind of interactions could be one of the reasons why we have starbursts in the universe. And so we're interested in understanding. However, can we tell anything about the physics of starbursts by looking at the spectral energy distributions that I just showed you? Can we associate those SEDs to particular stages of the interaction, or more important, to particular internal physics of the galaxies? That's the question we're trying to answer. And that's very pretty, but I guess I'll let you know. So, however, it's not an easy task, because starbursts are complex things. And this is a Hubble image of 30 Doradus, which was one of the objects I told you about before. And this was also one of the objects that Werner, for example, has been studying, and I myself had the chance to study from my PhD thesis. And the reason why starbursts are complex is that, of course, they are forming a lot of stars, very massive stars. And those, clusters of stars that form have a large, output of energy in the form of UV radiation that ionizes all the gas here. The reason why you see all those colors is because you are ionizing the gas. Then these atoms recombine and emit light. And then there's also a lot of dust that obscures. For example, here you see this dark region that's basically a bunch of dust that obscures what's behind. And then you have all that together, and you have to infer how that produces spectral energy distribution. When you look at galaxies, it's even more complicated, because if you try to take a spectrum, and this is an example from one of Werner's papers, if you take the spectrum of galaxies, of starburst galaxies, in order to take a spectrum, you need to put a slit in front of the galaxy and produce the spectrum. For many of these systems, the size of the slit, as you see there, pretty much encompasses all the galaxy, like in this case, or most of the galactic nucleus, where most of the star formation is happening. And then the information you get in the spectra that you get here is information containing everything, containing the stars, containing the dust and the gas. And hence, for most of the galaxies, you have unresolved information. All the information that you have from these systems is information that comes from the whole system. You cannot separate between the stars and the dust and the gas. And that will not even change a lot when we launch JWST, because even though this will be a large telescope, these type of regions like 30 Doradus will still be unresolved for distances larger than 30 megaparsecs. That in extragalactic scales is actually a very, very small region. And of course, if you look at this example, these are spectra obtained with the Spitzer Space Telescope. And you see, again, those walls you were talking about here, this is the pH emission. So that complexity reflects in a lot of different properties for the spectra. For example, these pHs here and the emission lines that you see here for atomic species, the slopes of the thermal emission are different. And then you want to try to get as much information as you want, both from the spectra and from studies at both short and long wavelengths. How do we measure how efficiently are these systems producing stars? Well, we measure the light. That's exactly what Elena told us before, that we astronomers depend on the light, and that's why we need to study all the radiation transfer things. We look at the emission of these systems in different wavelengths. This is an example. This is a normal star-forming galaxy. It's not necessarily starburst. M51 in a paper by Daniel Halsey, where you see the galaxy as it looks in different wavelengths. So we can trace the star formation by looking at those ultraviolet photons that are produced by very massive young stars. If you're looking at the photons that were produced by young stars, because young stars that are very massive and that are mostly responsible for the emission in these systems, they live short lives. And so if you're looking at those short-lived stars, you're also looking at the recent star formation, and hence you're measuring the very recent star formation. And so you can either look at the far ultraviolet, where these photons are emitted directly, which is the green part in this graph. You can also look at traces of ionization of the gas by these energetic photons, and then you can look at H alpha, which is the blue region. Those two have to do with far ultraviolet photons that get directly to us, except that in this case we're also absorbed by an atom and then re-emitted. And then you have an obscure part of it, basically regions of star formation that are behind very thin layers of dust. So this dust gets heated and then re-emits the light at far infrared. And you then have, from the infrared, you have information about the obscure star formation in this galaxy. You have, let's say, part of the star formation in these galaxies that is happening behind a lot of dust, and some star formation that happens and we can see it directly. So by combining those two, you can have an idea of the total star formation in a galaxy. Now, you don't necessarily need to limit yourself to study only these 3 bands. You basically can ask yourself the question, why don't we just look at as many wavelengths as we can to try to get information about the systems? And that's why you need a multi-wavelength approach. So different wavelengths you need to get information on these systems. Is there any questions so far? Am I going too fast? Maybe I'll just give it back to you. So we are lucky because in the last 10, 15 years, a lot of different observatories have been launched into space. And the reason why these observatories have been launched into space, I think we now all have it clear, is because all that trouble we have with the atmosphere that Bernard was explaining to us yesterday. In particular, for some of these bands, you cannot look at all from the ground, so you need to launch observatories to space. So here are a few examples of some of those observatories. So we have observatories that look in ultraviolet light, like ALEX. We also have telescopes that mostly look from the ground, that look at the near infrared. We have space telescopes like Spitzer that look at mid-infrared wavelengths. So these are the numbers, the wavelengths at which these telescopes can observe these galaxies. More recently, also the Herschel Space Observatory that looks all the way to 500 microns into the region of cold dust that thermally emits at those wavelengths, among a few others. So we have a bunch of data that we can now use to build the spectral energy distributions of these systems, and then by combining them with models and with clever ways to combine both models and data, we can come out with answers for the questions we have. So what do? You have a galaxy, again M101 for example, and then you want to measure all the flux that this galaxy is emitting at a particular wavelength. So you decide what's the size of your galaxy, and then you make an ellipse around it, and you measure all the flux that is contained by that aperture. And at each wavelength you do the same, making sure that your aperture is the same for a wavelength. This is not necessarily an easy task because you have different resolutions, different telescopes, etc., etc. But in principle you can do it. And so you can build this spectral energy distribution, but by making a point at each of the wavelengths where these telescopes observe, you measure the flux and you put it here all together, and you can build that spectral energy distribution from real data. Now you start seeing that looks a little bit like the theoretical spectra that I showed you before. You have the optical and UV here, and then you have something that looks like those bands of the molecules, the pHs, and then you have the thermal emission from the dust. And each of those regions is related to young stars or a bit older stars, or hot dust that is heated by massive stars, or maybe diffuse dust that is responsible for the emission in this part of the spectrum. So you kind of have a relation between the spectral energy distribution and the physics that is inside. Now the question is how you answer that question. Additionally, you can of course also take spectra of these galaxies, so you can put your slit and then obtain as well the spectrum, like the ones I showed you before here, that covers, in the case of the mid-infrared, covers this part. So what I'm trying to do is I'm trying to use all this information and try to answer the question why starbursts happen. What's different in the systems that they form stars of living. So what we do is SED fitting. So what we do is we have that SED that I show you the data, the points here, and you also have models. So people have thought about theoretical and empirical models that basically predict what the flux from these galaxies should look like at different wavelengths. And the idea is that you want to compare those two. And by comparing your models that predict certain values for certain parameters with the real observations, you can actually get information about these systems. So what most people, and then you find out of your models, for example, if you have a long list of models, and you try to see which of those actually fits the data better, you can just make a list of which of those models agrees with the data best. And that's what we do when we do chi-square minimization. You're probably familiar with that. You compare your prediction with your data and then see which of those models is actually closer to your data. However, that has significant caveats. First of all, because sometimes you have a limited amount of data. Even though we have a whole coverage here of all this emission, you still have a lot of parameters in this model. So sometimes you don't have enough data points to constrain all your parameters, so you want to find clever ways to do this. Also, the models sometimes are degenerate, which means that two different models with completely different parameters, or not completely, but somehow different parameters can produce a very similar fit to your data, so you want to understand those degeneracies between the models. There is usually no independent verification of whatever you derive by doing S&E fitting with what you actually so you don't have independent ways to test the parameters you get from, not always you do that. And then sometimes people care a lot about doing all the photometry fit and forget about the emission lines, for example, here that also contain very useful information about the gas and things like that. So we want to try to find different ways to answer the questions. Is that fit unique? Is that the only solution? Is that the more likely solution really? Are the parameters we're deriving actually describing our system? So we have adopted a particular set of models that were originally described by Dr. and later improved by Frank Rose to understand this system. So the way this works is we assume that a starburst is just a collection of H2 regions. What is an H2 region basically? Is a bunch of young stars, hot stars here, very massive stars that emit a lot of radiation, ionize the hydrogen and other gas species that are around here with the very energetic photons. Some other photons that are not so energetic or that are the product of recombination of these atoms go outside and modify the molecular material here, creating what we call photon-dominated regions, which is a completely whole talk by itself. But we assume that a galaxy, for example, that forms stars, is a collection of these objects. So this here would be the blue point would be the cluster of stars, and then this would be the H2 region. And you put a lot of them in a galaxy, and by summing up all the emission from these systems, because you're assuming that the galaxy is being dominated, the flux by this emission, you construct the total emission from the galaxy. And what do? We need several ingredients. We need, of course, to know how these stars emit their light. So you need to calculate the emission from these stars. So that's what we call stellar synthesis. We assume a population of stars, and we predict what the emission of these stars looks like, because that's the emission responsible for heating the dust, ionizing the gas, etc. Then we do what we call the radiative transfer. Because in the radiative transfer equation, we need to know how the light propagates through the gas and dust in this region. And we do that both for the H2 region and also the PDR that surrounds it. And at the same time, we're following the dynamical evolution of the system. So we basically, as radiation comes out of these systems, the radiation also pushes the gas and the dust out. And so this bubble expands in time, and you want to have a model that is consistent with that expansion. So this model takes into account all these things and is able to predict what the spectral energy distribution of the system would look like. Now, what kind of input parameters and what kind of output do you get from these models? Of course, as I was just mentioning, you have first of all the emission from the stars. So this is the result from your stellar synthesis. Then you also have the dynamical evolution. This is just showing you for different external pressures of the internal of the ISM, the interstellar medium. What is the size the change in the size of this bubble as time passes? So they basically increase because they expand, driven by the radiation pressure. And then you also have to take into account additional things. For example, some of these young stars are still embedded in very thick, individually, each of these massive stars is embedded in very thick layers of dust because this dust is still collapsing to form the star. And so you have a particular type of emission for these systems, and you need to include that emission from ultra-compact H regions. That basically represents, in an intuitive way, the very recent star formation. So the stars that are the youngest among all of them because they are still surrounded by dust. And then you get out basically BSED, in this case for different ages, because you follow this dynamically. So you can take BSED 1 million years after the star was started, and then all the way to 10 million years. Why only up to 10 million years? Because after 10 million years, most of the very massive stars have already disappeared. They have completed their life cycles, and they are not emitting these very energetic photons anymore. And then you also have, depending on how much PDR material you have covering the H2 regions, you also can calculate the impact of that in your SED. As long as contribution from not only with the very, very young stars, but also stars that are less massive and older can also contribute to the heating of the dust. And so you also include a component for that component of all stars. And so what do we have? And finally, I am forgetting about a very important thing, which is a very interesting parameter that is called the compactness parameter. And that has been one of the driving forces of my research. I'm probably getting tired to hear the word compactness by now, but I still like it. This is basically something that has to do with two things. If you have your H2 region, you have a cluster that has certain mass of the cluster, and then you have the ISM around it. And that ISM has certain pressure that tries to confine the H2 region. So you have a battle between the radiation from this massive cluster, and hence its mass, because the more massive the cluster, the more likely it emits, that tries to expand the H2 region, and the ISM pressure that tries to confine it. So the compactness has to do with that battle. It's telling you that basically, it's telling you how, in the balance of those two forces, at the end of the war, how close dust is to the stars, and so how hot this dust is, because if the ISM pressure manages to confine it to very short distances, then you have hotter dust, and as it goes far away, it gets colder and colder. So what happens is that what it's really controlling, the compactness was really controlling, is the heating flux of the dust. In other words, how much flux, how much energy per unit area is the dust receiving as time goes by. And you see that for different compactness, you have a different evolution of that heating flux. And the way that reflects in the spectral energy distribution is mostly by changing the position. We saw this morning about the black Corian, the deep low, and how as you move to hotter, dust temperatures, you have the peak of the emission at shorter wavelengths, and that's what you see there. So the compactness is extremely important at telling you where the peak of the emission is in these systems. And so it's a very, very important parameter. And it gets really interesting, and I still don't know how to use this. So what does it really mean? When an object is more compact, it's either, maybe you missed that, if an object is more compact, it's either because there are more stars there, or they are more massive, and so this parameter increases, or because the pressure around it is also more massive, or both of them. So those would be the two ways to increase compactness in a system, either by adding more mass here, more emission, or by adding pressure around it. So that's what compactness is all about. And so you have a model that predicts your spectral properties, and then you have a bunch of data. And you want to see what's the most likely model that describes your data. So you have your data and you have your model, and you want to see what is the model that has the highest probability of explaining your data. And so you have to find a clever way to compare data with models, because you maybe have a lot of different models, and you don't want to start comparing the chi-square for all of them. So a different approach would be to calculate somehow the probability that that model has to explain your data, and then see what's the model that has the highest probability. But since you don't want to do it for all the different models, what you can do is a random process. You can do what we call a Markov chain, that basically is a random it starts jumping from model to model until it converges by a clever way to change from model to model, something related to the random walk we were talking about this morning. And basically what you do is you start in a model where you can calculate somehow the probability, and then you randomly walk to a different model, calculate the probability of those, of both the initial state and the next step, and calculate the ratio of the probabilities. And if that ratio is greater than a certain random number between 0 and 1, you accept the step, otherwise you reject. And by doing that stepping process, you end up converging to a model that is the most likely one to fit your data. So this is the method I'm using to fit this data. And so that has an advantage. And this is where I introduce what we call Bayesian statistics. That you work with probabilities instead of having just a measure of how far your fit is by just measuring distances. You're actually talking in terms of probability. Actually, what the chi-square minimization is giving you is the probability that your data could be drawn from one of your models. So you're measuring what is the probability of your data given that those models are true. This is a concept that gives you the likelihood of the data being produced by your models. However, you can show that if your observational errors in those different bands are distributed in a Gaussian way, you can actually calculate that likelihood as the exponential of the chi-square distribution. So you can construct a probability, a likelihood for the data given the models, and then you use a very important theorem that was first discovered by a priest, a British priest, whose name was Bayes. And he, let's put it in a nicer way, this is how they have it at the University of Cambridge in the UK. This is what they call the Bayes theorem. And that is telling you that if what you want to know is not the probability of your data being drawn from your models, but the probability of your models, in this case called A, being true given your data, then you can obtain that by combining two things. The likelihood that you get from the chi-square distribution and something we call the priors. So this term here is just any information, contains any information you independently know about the parameters. So you have a model, for example, the star formation rate in your model, and you can constrain that somehow by looking at some other indication. So you can include that information there to update your probability and get a more likely answer to your problem. So this is how I do that. And the advantage of doing that is that the answer to your problem is not anymore a best fit, just this is the best model and these are the parameters, but actual probability distribution functions that tell you for the particular model, this particular model, parameter of this model, you have this probability, this kind of probability. And this is just showing you here that before you include any prior information, you have certain probability. Then you can include the prior, any information, additional evidence that you have from other sources, and that updates your probability until you can find an answer. And this is how I am obtaining the probabilities for my parameters. And I hope that wasn't confusing, but hopefully you will see it more clearly in a little bit. So the way we do is we have data, either spectra or photometry from stars or star-forming systems in general. And then you also have the models, the predictions, and you have the priors, and then you put all together in this machine, and then you get out the probability distribution functions for the parameters. So it's going to tell you how likely it is that the parameters of your model have certain probability to be true, given your data. And this is a very cool thing. So let's just get it to work before we fall asleep. So this is a first application of this method. We have been looking at interacting galaxies together with Lorraine Lance at the CFA, who has done a very nice job by taking a collection of about 40 interacting galaxies at different stages, as you see here, all the way from systems that are interacting, but maybe you see here only one of the galaxies interacting, but they are still far apart and they are not disturbed, so they have a very nice morphology. And this is observing the same galaxy for each of these three cases in different wavelengths: the ultraviolet, the near-infrared, the mid-infrared with Spitzer, and the far-infrared with Herschel. And then you have systems that are a little bit more disturbed. These two galaxies are interacting, and you start seeing the disturbance of the morphology. All the way to this particular example, what they call the antenna galaxy, where you have a completely disturbed morphology because of the interaction. So we have all of the data, including all the interaction sequence. And now we want to understand the properties of the system by looking at their spectral energy distribution. And so this is what we get. So we get fits, of course. So we have collected data for these galaxies. And this is, again, a galaxy that is in a very early stage of interaction. This is an intermediate state of interaction, and this is a very highly disturbed system. And then we fit with our models, with our method, those data. And what you get is that you need different contributions from different things. So for example, for each of them you need a different contributions of old stars. And when I say old, I mean older than 10 million years that contribute to the heating and to the emission in this part of the spectrum. And then of course, the more recent star formation that is basically heating the dust and producing the bump of far-infrared wavelengths. And you also have a contribution here from the ultra-compact H2 regions, those very, very young stars that are still embedded in dust. And by combining those three, you get the final SED. And I want you to realize that depending on the interaction systems, there seem to be different contributions from all of these systems. And now we're trying to understand how the global properties of these galaxies relate to the properties of the H2 regions within them by using the models I have explained to you. So this is how the actual probability distribution look like for a particular fit. So basically what you have here are the different parameters of these models. For example, the compactness, the star formation rate in the last 10 million years, the star formation rate in the last 100 million years, and the very recent star formation as traced by these ultra-compact H2 regions. And you see that what you get there is not just a best fit that is marked here with that sign, but a whole probability distribution function that tells you in the blue region at the 68% 1 sigma level of confidence what the value should be, or in the red area, except here that I made a mess with the colors, the 90% confidence region. So you know with 90% confidence that the star formation rate in the last 10 million years in that galaxy has been between 10 to the 1 and 10 to the almost 2, which seems a large range, but actually you can see differences from galaxy to galaxy. So these are what we're really interested in. And what happens if you take all your galaxies and do the same, and rather than just taking the best fit, you take actually the peak of the probability distribution. In other words, the value of the parameter where more models actually fit the data. That is a little bit more information than just a best fit, because a best fit can sometimes be an exception. And if you plot this ratio here is, for example, the ratio between star formation rates over the last 10 million years over the star formation rate over the last 100 million years, which if you assume that a significant part of the stars in the galaxy have formed in the last 100 million years, for example, we can consider there's a tracer of the specific star formation rate. What is the specific star formation rate? It's not only how many stars are being formed in these systems, but how many stars per unit of stellar mass. Because some systems can be forming more stars just because they are more massive in general. But if you measure the star formation rate per unit stellar mass, you have a better idea of the actual efficiency of these systems of forming stars. So you can consider that a tracer of that, and then you plot it against the compactness. What you see is that there is some kind of, if not very strong, at least some kind of correlation between those systems. And by the way, the colors there have to do with the interaction stage. So for example, these systems here that are blue are very disturbed, very strong interactions that are very bold, very mixed up, let's say, strong interactions. Whereas these yellow points here are, not very very strongly interacting systems. So there seems to be a relation between the specific star formation rate in a galaxy, the compactness, which you have to remember has to do with the average properties of individual H2 regions in this galaxy, and the interaction stage of these systems. So there seems to be, sorry, yes? Here come the difficult questions.
No. So the galaxy in the early stage of interaction.
Yes, the yellow and the red ones.
Lower specific star formation. But the blue one,
Yes.
they cover the old region.
Well, yeah, there is this one
And
here,
the
of
minus
course.
2 is very low.
Yeah, this is, let me say that we only have 40 systems here, and of course this is still not completely statistically significant, but there is certainly a trend for the blue points to be mostly on this part of the cloud than anywhere else. And certainly you have also this system. However, this system is interacting with this one, and there are some particularities about these systems which I haven't been able to study completely in detail one by one. But certainly you need a bit more of members to actually be able to say. But this is an interesting trend, and I will show you why in a second. Yes.
The compactness number have something about the shape, the classification of the
Well, that's exactly what seems to be the case. I mean, we're apparently the compactness, which is just measuring something related to the dust in the ISM inside those galaxies, apparently has something to do with where those galaxies are in the interaction sequence. So in other words, it looks like the overall, shape of the galaxy. In other words, the overall interaction stage is telling you something about what's actually happening to the dust at the level of the H2 regions inside, and that's interesting because you want to understand how star forming is happening, and the properties of the ISM will of course be very, very important there. So yeah.
How do you deal with the fact that HC is likely as an HEM?
Well, certainly that's a good question actually. So if you look at the I was told by Lorraine Hans, by the way, that none of these galaxies had an AGM, but I'm still going to answer your question.
Is it part of our 299, right? It's this veto system there.
I think there are only two, but you might be right. The point is, there's an interesting discussion there, and then that's the fact that heating at these wavelengths where the peak of the ultra-compact H2 regions is also where most of the emission would come if the dust is being heated not by star formation but by an active galactic nuclei. So to some degree you need to be able to disentangle if this emission here is coming from heating from AGN or star formation. We have tried to be careful in selecting galaxies that do not have an AGN, but it can happen. So we are using also different tools. There is a software called the Compire by someone in Heidelberg, I don't remember, that can take the same data and try to guess what would be the contribution from AGN. And we're trying to maybe at some point, if we are doubtful about a particular galaxy, subtract that contribution and then do this again. But in principle, that would mostly affect this parameter, at least for the photometric data. Of course, if you have spectra, it's a different story, but we'll come to that. So yeah, there can be contamination from AGNs, and it's important to keep it in mind. That's why I've been trying to get rid of all of your AGNs because I don't like them.
Martin,
Yes.
so I'm not from the same way, but I think it's some kind of counterintuitive to have a positive correlation among the star formation rate and compactness, since compactness, could be determined by the star formation rate itself. So if you have more star formation rate, so the system could be less compact because of the, pressure of the
No, I think that there's an important point there. I mean, it's the fact that you could say, obviously, there is more star formation rate. Of course, the the dust will be hotter because it's denser and blah blah blah. But keep in mind that the definition of compactness has to do with two properties. One, the average mass of the clusters of stars, and then the ISM pressure. So it's not only the pressure that comes into this. There's also something about the mass of these stars. And even if it's obvious, we haven't really quantified by how much the dust is hotter or more compact in systems that are starburst. But I don't know if what you meant is that you would expect star-forming systems or starbursts to be less dense. Is that what you were saying?
What I think is that if you have a large star formation, right, the region around the stars will be empty, will be almost empty, because all these stars will be allowing
after certain time has passed. Yes. And assuming that there is no extra gas coming in to form more stars. Okay. Because precisely the point is that these systems seem to be replenished by gas continuously for a certain period. So yeah, it's a good point. So there seems to be, I need to go a bit quicker if I want to say the whole thing. There seems to be some kind of evolution of the SED with the interaction sequence all the way from systems that are not very disturbed to all these systems like the one you just mentioned, which is very, very, very messy. And if that happens, remember that if that's the case, which we need to confirm with more objects, remember that these values I obtained by looking at the peak of the probability distribution function here, and not the best fit. Actually, if you repeat that plot and you use not the peak of the probability distribution function, but the best fit, it doesn't look that nice. And so I think this is a triumph of Bayesian statistics because it shows, that your parameters are maybe more likely in certain regions of your models, and it shows the correlations in a more straightforward way. So the important question there is this: is this evolution related to the internal physics at the level of the H2 region? So that's really the question I'm trying to answer. What are the implications of that relation if it's actually true? So remember that the compactness is just a combination of mass of the cluster and the pressure of the interstellar medium. So if dust is actually more compact, it means either there are more stars in these clusters, or that they are more massive. If they are more massive, that could have an implication, for example, in the initial mass function. The initial mass function is just the original distribution of masses with which stars form. I mean, if you form a bunch of stars at a certain point, how many of those stars are big and massive, and how many of them are small? If it turns out this increase in compactness is because of a mass issue, that could be maybe because there is a variation on the initial mass function. This is a strong statement, but it could be. Or gas is denser. Was gas already dense when the starburst started, or was it the interaction that by funneling the gas into it made the gas more dense and hence the compactness was higher? That would look like a more plausible explanation, but I will show some additional evidence that some of these will also be happening. And so are there actually two different modes? Is there a compact mode of star formation and a not so compact mode of star formation? That's the next question. And it was interesting because if you look at a little bit farther away systems, all these galaxies I show you here were galaxies, I'm running late, were galaxies that are local, are very close by in cosmic terms. But if you look at galaxies that are a little bit farther away, and this was some work by David Elbas a couple of years ago, he looked at the SEDs of a very large amount of galaxies at different redshifts. And he started looking at the average SEDs of those galaxies by using certain parameters. And he and his collaborators realized that there are two types of SEDs. And that this type of SED, that peaks at longer wavelengths is related to galaxies that are more extended, that form star in the disk in a more extended way, whereas these type of systems are more concentrated also when you look at the galaxy. So it's like if systems that are actually more compact visually are also having a hotter SED. So there seems to be, or at least from this evidence, there could be two different types of SEDs, and the question is this actually related to the compactness I was just telling you about? This could be a possibility. This is just to show you that those systems they actually have a slightly value of the ratio of the 8 micron emission to the total infrared luminosity. Those are the starburst mode systems in this paper. This is actually not so relevant, but in any case, it's compactness as defined by the Dopita and Gross models at the base of this difference. So this is an interesting question that we're trying to answer. So I'm going to skip this through. This was just applying, someone is interesting, the Kuiper's method to the actual L-bus spectrum, and we actually found something.
Rafael, can you ask that to see very close?
Oh, sorry.
Yes.
I get too excited. But let's continue very quickly to what happens where you actually, this is a different application of the method to other types of systems. So you can, as I mentioned before, you can do it for entire galaxies, or you can actually do it for starbursts within galaxies. And these are two examples of starbursts. This is the 30 Doradus region I was telling you about before in the Large Magellanic Cloud. And this one here is NGC 604 in M33. These are two local starbursts that are not covering the whole galaxy, but specific regions of the galaxy. And we can also use that. More than that, we this time are not going to be looking just at the let me skip this, at the photometry, but we're going to be looking, and this is something I did together with Bernard in my PhD. We're going to be looking at the spectra. We're trying to use the same method that I just described to fit the spectra, the Spitzer IRS spectra of the systems. And then you have there the spectra with the different, these are the molecules I was telling you about, and all the emission lines and the slope. And we're trying to fit actually all those features with our method and see what's happening. And then you can of course get fits to it, and in this case I have also included for some of the data from the Herschel telescope. And then we wanted to answer the same question: how well constrained are the physical parameters, and do they agree with what they know, what we know about these systems? And actually, you can look at the probability distribution function that we get for these systems, and this is to show you two important things. One, that when you try to fit a particular region of the spectra with your models, and you plot the probability of the mass having a certain value and the age of those systems having a certain value, you have significant degeneracies. There are two possible solutions maybe for this system. The best fit is here, which in this case coincides with the peak of the probability distribution function. But there is also a very likely answer here, at least for the case of Teridor. In the case of NGC 604, we see it less. And I'm pretty sure that has to do with the fact that in this case we also have the Herschel data that helps us constrain those values a bit better. More importantly, if you include the nebular lines, so the emission lines, you don't worry only about the continuum emission, but also about the nebular lines. If you try to do the fit without fitting the emission lines, so only the continuum, you see that you get a similar distribution of the probability, but the peak is somehow here, the best fit is kind of lost. If you do include the lines, then you suddenly make your solution converge to an actual value. So including the emission lines, it's giving us very useful information, for example, about the age of these clusters, of these edge regions, because it's telling us about how intense the radiation field is, and that helps us constrain these systems. We realized that pointed us to significant, well, maybe not very significant, but certainly we could constrain difference in the evolutionary stage of these systems, which were differences that we knew about in advance. This was done at an earlier stage of the project where we wanted to actually know if this made sense. And in general, we found that there is evidence that as we know, NGC 604 is a little bit more evolved than 30-door, and that is an independent confirmation of our method. So that's very useful. We also measured the contribution of very recent star formation in NGC 604. So this is NGC 604 received at the Spitzer bands. And you see that there are certain blobs there of star formation. And you can measure the star formation in these blobs using this method. And we measure that even though the star formation, the current star formation as traced by the ultra-compact distributions is much less in NGC 604 than in 30 lower, you still have that the very recent star formation accounts for about 8% of the total star formation rate in NGC 604. And then finally, we also looked at, just to finish a different application, we looked by the end of my PhD thesis at some starters of the selection by Bernard 2006. And we were also looking at trying to constrain the Spitzer spectra using this method. These were also systems that we thought had no AGN. And about the interesting thing about this, we could of course get fits to it. And one interesting thing is that even though this is a very small sample, we found several things. Well, first of all, there's a good correlation between the star formation rate we derive from these systems and the amount of molecular gas available, which points to a star formation law. You form more stars when you have more gas available. But also the systems that are more compact tend to be the systems that have the lower limits in pressure. So in order to have a common, you know, in order to keep the compactness at a certain rate, if you have less pressure of the ISM, then you need the clusters to be a bit more massive. And so, since also the systems that had that particular correlation that indicated that actually the clusters were more massive, were also the systems that had stronger emission lines, we thought that maybe, and this was a little bit of speculation, but we thought that maybe that meant that actually those systems are forming more massive clusters. And that brings me back to the discussion of whether or not the compactness issue has to do also with mass variations of the clusters. And if we could actually do a large sample of these systems by measuring a lot of spectra and see if there's a correlation between compactness and pressure, that tells us that in some systems the clusters are more massive, and if those systems happen to also be the more active ones in interaction, for example, then we could maybe come to an answer regarding whether or not the mass of the clusters is playing a role in the compactness discussion. So this is what I wanted to show you. So I'll just leave the conclusions there, and I will tell you about JWST later because I want you to have some rest. Thank you very much.
I want to know, these are very general questions, but I want to know how these Star Wars fits in the whole picture of the galaxy history. I mean, we know that the galaxies are ensembled by merging small pieces. So we should have in the past in the galaxy a lot of Star Wars regions. Right. So how these processes contribute to the evolution of the kingdom?
Yeah, this is as I said, most of the stars that we see today were formed, at redshifts of 2.5 or less, and there was a lot of interaction going on in the past. Actually, very luminous objects like ultra-luminous infrared galaxies were way more common in the past, in the early universe, than they are today, which indicates that there was a moment in the history of the universe where either interactions were very common or something was different in the ISM that was making these galaxies more brighter at infrared wavelengths. And actually, one of the interesting things that Elbas found in that 2011 paper is that whereas most of the starbursts, in the local universe, most of the galaxies that form a lot of stars have the starburst-like spectrum. In the early universe, most galaxies were forming a lot of stars in the main sequence mode. So they were apparently forming stars, in the disk and not in a very compact way. So there is certainly a relation between what happened in the past and how we understand the universe.
And that brings me to the second question. Sorry, I just have this question because I'm very concerned with planetary formation. And I asked the past this, but I'm very worried. I'm concerned about the fact that if we had a lot of star bursts in the galaxy, probably a lot of stars formed in that region that are presently still alive could have probably lost their protoplanetary disks because of the evaporation inside a very bright giant cluster in the star burst. So maybe we are overestimating the amount of planets, probably if we take into account. So I want to know if we have some figure, if we can detect some star and say this star probably formed in a star burst.
I think there are some people who have written papers about whether or not planets form in clusters, very dense clusters, things like that. I don't know much about what the results are, but it's certainly a good point. I mean, and at some point, if there was, a planetary system that you find very close to a cluster, then that would be interesting. But we could definitely think about something in that order. Yes. Anyone of the students want to know anything, or was it so boring? No. Yes.
Pero en español.
Go ahead.
No, pero es con respecto a una imagen que tenía en el anterior, que eran donde habían como 9. No, o sea, no hay imágenes, atrás, no.
Ah, las galaxias. Okay.
Ahí, esa, viendo que las de Herschel, esas dos de arriba, hay una que es amarilla, que imagino que es por, no sé, ¿es de qué?
Ah, bueno, los colores aquí son un poco arbitrarios, digamos. Todas estas son 3 galaxias diferentes vistas por Herschel. Y los colores tienen que ver un poco con la diferencia en la contribución de las diferentes bandas de Herschel, porque Herschel observa varias bandas, a 70 microns, a micrones, a 100 micrones, a 160 micrones. Y entonces la contribución de cada una de esas bandas tiene que ver un poco con la temperatura del polvo y eso. Eso hace que esos colores sean diferentes. Entonces eso tiene que ver con las variaciones en la temperatura del polvo en estas galaxias. Pero lo que nos interesa ver es qué tanto emiten estas galaxias en el infrarrojo lejano, qué tanto emiten en el infrarrojo medio, en el infrarrojo cercano y en el ultravioleta. Pero si los colores tienen un significado allí, generalmente tiene que ver con temperaturas en la diferencia de la temperatura.
¿Y por qué la de la esquina es más borrosa que las de la misma galaxia?
Porque están más lejos, probablemente, y el telescopio tiene una resolución específica, y obviamente un objeto que está más lejos lo ves con menos resolución. Como cuando ves a alguien muy lejos no distingues bien la cara, lo mismo pasa con las galaxias. Lo que pasa es que aquí las pusimos más o menos del mismo tamaño, pero en realidad esta está mucho más lejos.
But that means that in this case, Spitzer have better resolution than Herschel.
Yeah, definitely.
Because the wavelength also.
Right. So Spitzer observes, even though the mirror of Herschel is bigger, the wavelength at which Herschel observes is longer, and the resolution and wavelength are related. So, as Bernard has, yes.
Yes.
Wait until on the 10 hour, and you will know the answer. Yeah.
I have a very simple math question.
Okay.
I was confused by your last statement where you were speculating about the connection between compactness and mass of the cluster.
Yeah.
Now, I thought you defined the compactness as the log C is the sum of log cluster mass plus log P on K.
Correct.
In your table at the second last slide showed that there was an anti-correlation between C and P on K. So that seems to me that it means that P on K doesn't matter at all, and your compactness is simply another measure of the cluster mass.
And also you show anti-correlation.
is on the emission lines. And I have to tell you also that even though the emission lines have turned out to be very useful, they are not as well reproduced by the models as the continuum. And so I'm not 100% sure that the continuum studies only will tell us. However, I see your point, and I think the pressure issue needs further study. I just took whatever pressure I got from models and I took the lower limits. And I looked at the lower limits and how the lowest possible value was in comparison with the compactors. And it was that relation. Now, I have also to remind you that by the time I wrote that, I had one month left to finish the PhD. So I'm a little bit in a rush. But I think by looking at the spectra and trying to constrain the pressure a little bit better, if we can come out with a clever way to relate the three quantities, we could actually break this compactness degeneracy between mass and pressure, and that would be a cool thing to do. But it's a fair point.
And there was also a very clear anti-correlation with star formation. But this the most
for these systems. The problem is that for these systems I only use the spectra, so I don't have any information on the near-infrared where most of the older populations are. And hence I don't have any information to constrain specific star formation rate, which is what really matters. This was only star formation rate, but some of these galaxies are just more massive than the others. So you need to take this into account. Anyway. Thank you very much.